Hi, and welcome to Module 2 of Lecture 2. In this module, we're going to continue this discussion of the central limit theorem we had in Module 1. So to remind you all what that was, the central limit theorem says that the sampling distribution of sample means will approach a normal distribution with a mean equal to the true population mean mu and a standard deviation equal to the estimate of the sample's standard deviation, sigma hat, or S, divided by the square root of n, where n is the size of the samples. The standard error tells us the uncertainty in our estimates of the mean without our having to pull hundreds of repeated samples. And that's the key here. That's the really important part. Because we know statistically from the central limit theorem that the sampling distribution will have a mean equal to the true mean and a particular set standard deviation, we don't have to pull 1,000 samples to draw out the whole sampling distribution. We can just pull one and assign an error to it. So, and again, the standard error of the mean is this. The standard error of the mean equals the standard deviation of the sample over the square root of the sample size. So, the great part about this is we can take a single sample and get an estimate of the population mean and an estimate of how confident we are in that mean. And we can see that as our sample size gets larger, our confidence increases because our standard error decreases. Just to show you that in more depth, right, the formula for the standard error was sigma hat over the square root of n. That has the sample size n in the denominator. So as the denominator increases, the fraction becomes smaller, right? So this is the example of how you increase the denominator, decreasing the overall fraction, and therefore decreasing the standard error as the sample size increases, right? And remember, smaller standard error means a sampling distribution that's more tightly focused around the true mean, and therefore greater confidence in our estimates, because we have confidence that any sample mean we happen to draw from any particular sample we could take would have a mean pretty close to the true population mean. That increases our confidence in our samples. So let's go back to the example from last time. Remember, the Democratic candidates received 52.5% of the vote in congressional elections on average. That was this distribution in the population. We can take a sample of 1,000 elections, get a mean of 51.58. This is 0.92 off the true mean. Now remember, we won't normally know that. We'll only have the sample mean. We won't know the population at all. We could take a standard deviation of the sample of 1,000, and then we can use that formula we had before to calculate the standard error of the mean in that sample. So it's 16.035 divided by the square root of 1,000, which is about 0.51. That's our standard error. Because we have the standard error, we can know that the sample means, because we know the sample means are from a normal distribution, we can talk about a confidence interval. So let's define that. Because the standard error is the standard deviation of the sampling distribution, we know that 95% of the sampling distribution will lie plus or minus about 2 standard deviations from the mean. If you've forgotten that, you go back to the previous set of slides and look at the area under the curve. So 95% approximately of the sampling distribution lies about 2 standard deviations away from the mean in either direction, given a large sample size. And 1,000 is definitely large enough. So how do we write that differently in a little more mathematical way? Well, to calculate the confidence interval of the mean, we need to know the mean we got in the sample, the standard deviation of the sample, and the size of the sample, or the standard error of the sample, which uses both pieces of information here. So the confidence interval is the mean plus or minus 1.96, close to 2, times the standard error of sigma hat over the square root of n. Right? Another way of writing that is by writing out the interval in which you're confident in. So here the interval is x bar minus 1.96 times the standard error to 2x bar plus 1.96 times the standard error. So this is the range, this is the confidence range here. And the 1.96 is chosen to be 95% confident. So again, going back to confidence intervals here, our sample mean was 51.58. The standard error we calculated was 0.51. So we are 95% confident that the population mean lies between these two values. So those two values, those two values are obtained by looking at 51.58 plus this and minus this. So here's the range. Now note, the true value, if you remember, was 52.5, so it's just barely in that range. So we actually got, our sample here is actually a fairly unlikely sample to have drawn given the true value. But it's still certainly possible. Also note that the fact that 95% of the population is likely to be in this range still means there's a 2.5% chance that the population mean is smaller than the end of that range, and a 2.5% chance the population mean is larger than that range. What if we did this for a smaller size sample of, say, 100? And we got a different mean and a larger standard error. Well, the standard error is larger because we've cut down the sample size from 1,000 to 100. So the denominator is smaller by a factor of the square root of 10. Now our new confidence interval is 47.99 to 54.68. So it's a much wider confidence interval. Because we have a smaller sample size, we are less clear about where we would draw a mean given a particular sample that we had. So to compare them, head to head, when you have a smaller sample size, we went from about 48 to about 54.5. For a bigger sample size, it's about 50.5 to 52.5. So you're less confident where the true mean is with a smaller sample size. With a smaller sample size, the standard error is larger. How large should we go in general? Well, the standard error takes a big, fast dip as you increase the sample size from 0 to about 100, and then it reduces much more slowly as you increase the sample size further. So this is a particular example with the sample mean at 50 and the standard deviation at 10, but in general, if it's true, you get a big, big benefit for increasing sample size when it is small, and the benefit levels off over time. So getting to about 100 really massively improves your situation. Getting past 100 does it less so. That's it for this one. We're going to take a little break after this one to go into some of the underlying math in the next module.